So this video is an explanation on TDRs and how they work and what you would read from them in different cases depending on the termination scheme of a transmission line. But first, in order to know what a TDR is, you have to know what a transmission line is. Transmission line is either a very long regular wire that introduces a characteristic impedance, or it is a very short but very high frequency wire. And it's basically a theory where if the length of the wire is larger than 1/10 of the wavelength, you're gonna have to use this. And it's different from a basic circuit because when you introduce transmission line theory, you start to have reflections. So when this travels through, the load is going to reflect something back with a reflection coefficient. At steady state, the transmission line goes away and it starts to behave like a regular circuit, but before then it starts to reflect. Time domain reflectometer, TDR for short, is basically a voltmeter for a transmission line. It measures the reflections from the load side at a very fast scale, a nanosecond scale, because the transmission line goes to steady state pretty quickly. An application for using this TDR is to check if there's any faults in the cable or to see if you're matching the impedance of the transmission line correctly. TDR is also able to estimate where the fault is, if the fault is in the cable, if there is one, by using one of the key parameters you put into it, which is a velocity factor or a velocity propagation speed, and it's able to use that to calculate the distance in which the fault occurs. You're going to see different graphs on the TDR for different termination schemes, and for the first case, this is a simple termination, resistor termination, and this is the reflection coefficient. You see that if ZL is equal to Z0, this reflection coefficient will go to 0, and so there would not be any reflection, and it will just be a straight line on the graph here. But in this case, we're going to assume that ZL is going to be 2 Z0. So this reflection coefficient is going to turn out to be 1/3. What you do with this 1/3 is that you multiply the original input, which would be 1/2 VG, and that'd be 1/6, and you add 1/6 VG during the first reflection, and as the transmission line goes to steady state, it is going to go to 2/3 VG for the first case. Now if this was negative, you'd subtract it, so you'd go down instead of positive, you go down this way. Okay, so for the second case, termination is a capacitor and it's active. So the reflection coefficient, let me find a color, is ZL minus Z0 over ZL plus Z0. So for a capacitor, it will act like a short first. So this will be 0 and this will be 0, so it's gonna equal -1. And because it's gonna equal -1, you're adding it to 1/2 VG. And 1/2 VG minus 1/2 VG is gonna go to 0. That's what short's gonna do. And then as this approaches steady state, the capacitor becomes an open. So instead of this being -1, it's going to be infinity over infinity. So it's going to equal 1 for an open. So as it goes to steady state, it's going to go to 1/2 VG. And then it's going to go up all the way to VG, because you're adding it to VG now. And that's what a capacitor does. The third case is the inductor. An inductor will initially act like an open. And so if the inductor is an open, the coefficient is going to be infinity over infinity, which is equal to 1, so fully reflect. So you're gonna have the 1/2 VG, and as it reflects, it's going to go up, multiply Vn by 2, and then this will be VG. Then as this approaches steady state, the inductor acts like a short. So it's going to exponentially, it's not really exponential, but it's going to exponentially go to 0. Okay, for case 4, we have these 2 transmission lines connected with a resistor, match resistor, and a capacitor. And the graph is going to be, as always, starts at 1/2 VG. This capacitor is going to look like a short, so initially the current won't go through this transmission, it will just go through this short, and TDR is going to see this initially, and it's the match, so there's no reflection initially. And then as this capacitor transitions to an open, it's going to start going through here, and Z0, there's going to be 2 resistors here compared to this, so this is going to start approaching exponentially 1/3 VG, because this will turn into an open, and as when it gets to steady state, it's going to be a resistor series with a resistor. The transmission lines disappear, so it's going to be resistor, resistor, and ZG, and it'll be 1/3 VG. Okay, and for the last case, case 5, we have an inductor where the resistor was and a resistor where the capacitor was. The inductor will start out as an open. So again, 1/2 VG. This is going to open, it's not going to see any of these. For the first reflection, it's not going to see any of these. It's going to start out as an open, and so it will go up to VG, and then as it starts transitioning to a short, it's going, at steady state, it's going to have Z0, ZG, Z0, which are all equal, so it is going to go down to 1/3 VG when you go to steady state. So yeah, That is TDR and some basic terminations. I hope you enjoyed it. Bye.